Hello and welcome to this lecture. In this lecture, we are going to do a few simple hypothesis testing problems where a test is given to you and you have to go ahead and compute the significance level and the power of the test, etc. So, the probabilities of type 1 error, type 2 errors. It will give us good practice. You will see various different distributions come in. You have to use knowledge of probability, being able to compute, etc., etc. Okay. So, here is the first problem. This is similar to the example that I considered for motivating this problem. There is a possibility that a coin could be authentic or counterfeit. If it's authentic, probability of heads is 0.5. If it's counterfeit, probability of heads is 0.6. You're tossing the coin 100 times, okay? And now I have this 100 possible outcomes. I have to carve it up into an acceptance set and a rejection set, and look at how something is being done here. This is something clever, and this is done all the time. You first figure out some simple statistic on the samples. Okay, so here in this case, what's probably most interesting is the number of heads seen. Okay, so T we take as the number of heads seen in these 100 tosses, and then we will design the test or decide the acceptance set using T. Okay, so what is the T here? T is number of heads, and what is A here? The set of all outcomes or samples of samples, right, such that T is greater than C. Okay. So, this is how we decide, okay, so this is the test that rejects AC. So, the acceptance will be less than or equal to C. Okay. So, this is going to be my acceptance set design. Okay. So, I have my outcomes. I toss my coin 100 times. I got my outcomes. I will count how many heads I got. And then I will have some constant threshold value C. Let's say this value is 55, okay, some value that I come up with. Okay. If the number of heads is less than or equal to 55, I am going to say that the coin is authentic. If the number of heads is greater than 55, I am going to say the coin is counterfeit. Okay. So, this is how I am defining my acceptance set. Okay. It is defined using one random variable capital T, which is some statistic that I derived from the samples. Okay, it's a function of the samples. It will have a distribution. In this case, T has a binomial distribution, 100 comma probability of heads, whatever that value is. And the C is a constant, right? So, everything is going to depend on C. Your significance level is going to depend on C. Your power is going to depend on C. Okay. So, this is how you calculate it. It's not very hard to imagine this. C is a very important number, right, and you have to choose your C. Knowledge of C is very important, and that's what you're going to do. So, let's compute the significance level of the test. What is significance level? Let's what we've been denoting as alpha. What we've been denoting as alpha. It's probability that you reject H naught given H naught is true. Okay, so this is a convenient way to write it. Now, remember, H naught being true, all that it means is probability of heads is 0.5, right? Okay. Given probability of heads is 0.5, what is the meaning of reject H naught? Outcome belongs to A complement. So, this is nothing but probability of A complement given that the probability of H is half. Okay. So, what is A complement? T is greater than C. Now, remember, T has a distribution which is binomial of 100 comma probability of heads. Okay. So, it's 100 comma half. So, it's summation k equals C plus 1. We will imagine C is an integer. Okay. It's greater than C to 100. 100 choose k, half to the power k, and then again half to the power 100 minus k, and you can write half to the power 100 if you like. So, this is the significance level. So, as you vary C, alpha is going to vary. Okay. So, as you keep changing C, alpha will vary, and you can pick your C to get a particular value of alpha. Okay. So, usually what you do is you fix an alpha and find C. Okay. C that satisfies the above relationship. Okay. So, you keep changing the C, go to a C which has this value satisfied. Okay. So, supposing it satisfies for a particular value of C, you know that if you keep increasing C further, also this same alpha will be satisfied, as in you will get a value lower and lower and lower. Okay. So how do you pick C? You may want to think of the power of the test, which is this beta, which is probability of rejecting, accepting H0, or anyway, I need to compute the power 1 minus beta. So let's just do this. It's good to keep it like this. Under HA, what's the probability that you will reject it? It's a good thing, okay? Power is a good thing. It's a good probability. You want to maximize it. This makes probability of H 0.6. This once again means outcome belongs to A complement. So here probability of A complement given probability of heads equals 0.6. It's sort of the same expression, k equals C plus 1 to 100, 100 choose k, 0.6 power k, 0.4 power 100 minus k. Okay. So now I want to maximize this, okay, and maximizing this will need C to be as low as possible, right? So you fix an alpha and try to find C. You see that you can go up to a certain C and you can keep going beyond it also. You will get lower and lower numbers. But if you want to maximize the power, you want to go find a C, which is as high as possible. Okay, so because the more the C, the higher this value will be. Okay, so higher C implies higher power. Okay. So from this it appears that a good thing to do is to fix an alpha, find the smallest possible C. No, I'm sorry, I got this wrong. Lower the C implies higher the power. The least value of C, you want more and more and more terms here, right? So the lowest possible C gives you the highest possible power. So this is important to know. So you fix an alpha, you go find a C which will the lowest possible C which will satisfy this, and then you will get the answer. So the overall strategy is fix alpha, find lowest possible C, and that ends up maximizing your power also. Okay, so you notice here how once you design a certain test, and notice the smart way in which we use the number of heads to design the test. Instead of just writing down the set or anything like that, you just compute the number of heads and make everything depend on the number of heads. Okay, so that's problem 1. Anyway, the moral of the story is it's very, very simple. Given a acceptance set, try to find the distribution for anything involved and try to simply find alpha and beta. Probability of A complement given the null hypothesis is true, probability of A complement given the alternative hypothesis is true. Okay, so this is the significance level, this is the power. You should be able to just write down the probabilities for these type of descriptions. Okay, you may not be able to compute it and all that, but at least writing it up, you should be able to write up very cleanly. And we are able to see that once you write it up, you can argue about how to go about choosing any parameters that are missing in the test. Okay. Okay, so let's move on to another type of problem. In this case, we have a normal distribution. There is only one sample. Okay, so some things are simple when there are one sample. But we expect the sample to be from a normal distribution with mean mu and variance 1. Variance is also given to you. There are two hypotheses about this distribution. The first null hypothesis says mu is -1. The alternative hypothesis says mu is +1. Okay, and I'm going to consider a test. What is my test? My test is going to look at the sample X, and if it is greater than C, it's going to reject the null hypothesis. Okay, so what is my acceptance set S? It's the set of all X such that X is, let me just write it in terms of capital X, X less than or equal to C. Okay, so this is good enough. So if you want a pictorial sort of representation, you can imagine a C here, and then everything on this side is A complement, everything on this side is A. Okay, and you know the distribution is normal with mean mu equals -1 under H0 and mu equals 1 under HA. Okay, so this is the acceptance set. I hope I got that right. Reject if it is greater, so accept if it is less than or equal to. Okay, once again you have to find the significance level. These kind of questions are not too difficult, but you have to just write it down very patiently. So alpha is probability of A complement. I'll cut short some of the work before. A complement given the null, which is mu equals minus 1. Look at how quickly I am cutting short all the detail that I did last time. It's probability of rejecting the null given that mu equals minus 1. Okay. So this is what. So once again, a picture might be true, might be good. Mu is minus 1, so your distribution looks something like this, and let's say your C was somewhere here. Oops, the distribution is something like this. C is somewhere here. A complement is x greater than or equal to C, this distribution, right? So this area is being asked here. Okay, so this is alpha, right? So mean is minus 1, right? Because null is true. Okay. So this you know how to do this. So it's the probability that a normal distribution with mean minus 1 and variance 1 is greater than C. Okay. So how do we do this normally? This kind of a calculation, we will convert this normal distribution to the standard distribution. So this is the same as the normal distribution. So, okay, let me just write it carefully, minus 1 comma 1. So it's just this normal distribution minus 1 comma 1 plus 1 by the standard deviation, which is just 1 greater than C plus 1 by 1, right. So this is just to get it to the standard form. So this guy is the standard normal. Okay, you can keep it as Z. Z is something that we use for standard normal. So this is probability that Z is greater than C plus 1, and that is the same as 1 minus Fz of C plus 1. Okay, so Fz is CDF of standard normal. Okay, so this is something that we know already, right. So it's 1 minus Fz of C plus 1. So that's your alpha. Okay, so notice how easy it is to, just given the test precisely defined, it's very, very easy to compute these alpha and beta. Okay, so what is power of the test? 1 minus beta, probability of A complement given mu equals 1. Okay, so once again you can draw a picture here if you like. So this time the mean is going to be plus 1. Okay, so maybe the C is still here, and probability of this guy, right. So that's what it is. So it's probability of the normal with 1 1 greater than C. So you can imagine what you have to do. Probability of n 1 1 minus 1 divided by 1 greater than C minus 1 divided by 1. Okay, so it's probability that Z is greater than C minus 1, and that's 1 minus Fc of C minus 1. Okay, so that's it. So those are the two expressions. You can imagine how you will go about deciding alpha and C. How do you decide C? Okay, so you fix an alpha, you go ahead and pick the C that you will get, and in general you want to pick the lowest possible C. You don't want to pick a very large value for C. The lowest value of C that you can do, you want to pick. Okay, different values of C will give you a different hypothesis test, different significance levels, different power. Okay, so that's the idea. So always a trade-off, and you have to pick something in the middle. Okay. For instance, let me just dwell on this example a little bit more. You could pick C equals minus 1. Okay, if you pick C equals minus 1, you will get alpha equals half, and you will get a certain value for beta. Beta is 1 minus Fc of minus 2. Okay, so whatever that value is, you will get. So you can see, I mean, as you keep increasing C, maybe you want to pick C to be equal to 0. Okay, this is an interesting thing, right? Minus 1 and 1. You want to look at the value of x and decide between minus 1 or 1 as the mean. Maybe 0 is an interesting thing. So in that case, you will get alpha to be 1 minus Fc of 1, and then beta is 1 minus Fc of minus 1. Okay, you can imagine what this is. Remember, Fc of minus 1, it's the CDF of the normal. Fc of minus 1 is going to be 1 minus Fc of 1, right? So you can see alpha and beta are related as 1 minus each other at C equals 0 and all that. So you can see different possible cases. and you can imagine how this would work out in practice. Okay, so this is just one sample, so it was quite easy, and we came up with a test, and we looked at the significance level and the power. Okay, problem number 3. In this case, we have one sample from a binomial distribution, 100 comma p, and this p is unknown to us. And I'm going to modify things a little bit, make it a little bit more interesting. There is a null hypothesis and alternative hypothesis. The null hypothesis says that the coin is fair. Okay, what do I mean by fair? P equals 0.5. Okay, the alternative hypothesis is the coin is unfair. Okay, so this is starting to become a little bit more interesting, isn't it? So instead of saying 0.5 and 0.6, what is that 0.6? I mean, I really, in most cases, I need to know whether the coin is fair or not, right? So here is a very interesting hypothesis. Supposing you toss the coin 100 times and you observe one sample from that binomial distribution, which is number of heads you got or something like that, right? So imagine like that, and then you have this hypothesis that the coin was fair. That's your null hypothesis. And there is an alternative hypothesis that the coin is not fair, and that depends on p. I don't know what the value of p is. It could be some p not equal to 0.5. Okay. Now I'm going to consider a test that rejects the null hypothesis if x deviates too much from 50. Okay, right? That's a reasonable test if you think about it, right? So p is 0.5. If you expect p to be 0.5, then the average number of heads you should get should be around 50. So if the absolute value of x minus 50 is greater than 10, I'm going to reject h naught. So once again, draw it in the picture if you can't get this very cleanly. So you have x minus 50 being 10, so it's 60, 40. Okay, so within this you accept the hypothesis, and then including 40 and 60, by the way, and outside of this you reject. Okay, so you reject h naught, you reject h naught here also. Okay, so the coin is unfair if you do this. Okay, seems reasonable, right? So the acceptance set A is 40, 41, so on till 60. Okay, so how do you find the significance level of this? So notice, for finding the significance level, you only need probability of A complement given p equals 0.5, right? So what is that? So you're going to add up k equals 0 to 39, 100 choose k, and this is just half, right? So it will be half power 100 plus k equals 61 to 100, 100 choose k, half power 100. Okay, so these two are actually equal. You can compute if you like, but this is what you're going to get. Okay, so this is your significance level alpha. Is that okay? So to find the significance level, notice you only need the null distribution and the acceptance rejection region. You don't need the alternative distribution at all. Okay, so think about why that came about. Okay, so it's only type 1 error. I'm trying to find out when will I reject the null, when the null is true. So if the null is true, you need only the null distribution. You don't need the alternative distribution. Okay, so that's a good thing to know. Okay, now what about the power? The power will actually depend on p. Okay, so you can't do power without p, because the reason is it depends on the alternative hypothesis, right? So whatever p is, you will need that value of p. So let's just do that here. So if you want the power, it's probability of A complement given some value p for the binomial distribution. I don't know what that p is. So you're going to have summation k equals, no, let me just write it differently. Probability that mod x minus 50 is greater than 10 given p. Okay, so this is the distribution. So you can use the normal approximation if you like, right? So so what is the variance, right? Variance is so expected value mean is 50, variance is 100. It's not 50. It's sorry that mean is 100p and variance is 100p into 1 minus p. This is asking for absolute value of x minus 50 greater than 10, so there is this 50 here, so maybe we can look at it as probability of x is greater than 60 for p, and then probability of x is less than 40 under p. So then you can, you know, sort of use the so x is approximately normal with mean 100p and variance 100p into 1 minus p. We are going to use this. So if this is normal, you'll rewrite it in the other way, right? So you're going to do x minus 100p by square root of 100p into 1 minus p is greater than 60 minus 100p by square root of 100p times 1 minus p. So this is just a standard way in which we do the computation. X minus 100p by square root, writing it over and over again. So anyway, let's just do it. 40 minus 100p by square root of 100p, oops, 1 minus p. Okay, so this seems simple enough. So now I'll do the approximation. So this I will take approximately to be normally distributed. Okay, so then I'll say probability of normal 0, 1 greater than this guy I can't live without. Okay, remember this 100 maybe square root is 10. 10 will sort of cancel here, so you have 6 minus 10p by root p times 1 minus p. Okay, so this looks nice to me. Probability of again normal 0, 1 is less than 4 minus 10p by root p times 1 minus p. Okay. So depending on the actual value of p, you will get different values here, right? So this is what this is 1 minus fc of, right? Z is my normal 0, 1, right? This is my standard normal, and fc of 6 minus 10p by root p 1 minus p plus this is just fc of 4 minus 10p by root p times 1 minus p. So you plug in your value of p, you will get a certain power. Okay, so the power will vary depending on p, whatever your actual alternative hypothesis is, and it's difficult to make any more statement much more precise than that. As p becomes closer and closer to 0.5, you will get the alternative distribution being very close to the null distribution. It's difficult to distinguish between the two, etc. But other than that, this will give you the answer. Okay. So once again, I want to convince you the situation may be a little bit complicated, but once the test is defined, once the null distribution is known, once you know the alternative distribution, it's relatively easy to compute the significance level and power of the test. Okay, let's do one more problem, which is maybe a little bit more complicated, a little bit more typical. Okay, so this is the same normal mu1 distribution, but in this case, we are going to observe 100 IID samples of the normal distribution. Okay, so the mean could be -1 or the mean could be 1. The noise variance is 1. Okay, and you have to decide whether the null hypothesis is true, which is mu equals -1, or the alternative hypothesis is true, which is mu equals +1. Once again, we'll consider a test statistic T, as they call it, which is the sample mean. T equals x1 plus x100 divided by 100. It's the sample mean. And again, I'm going to use the sample mean to determine my acceptance region. Okay, if T is greater than some constant C, I haven't fixed my constant, whatever that constant could be, I will reject the null hypothesis. Very, very similar picture to before, except that T now is normal with mean mu and variance which is not 1, it is 1 by 100. Okay. So that's the trick to it. We know normal distribution, if you do n IID samples and take the sample mean, variance is going to be the original sample divided by 100. So variance has gone down significantly, and that is something that we can use. Okay. But other than that, the acceptance set is exactly the same. T is less than or equal to C. Okay. So the acceptance set is exactly the same. So if you want to find alpha, its probability of T being greater than C given mu equals -1. Okay, mu is -1. What's the probability that T is greater than C? Again, it's mean mu and variance 1 by 100. Mean -1 and variance 1 by 100. So, you are going to take this and you are going to do this probability of t, t is normal, right. So, it is going to be, let me write it properly like this, normal minus 1, 1 by 100 plus 1 by 1 by 10, right, is greater than c plus 1 by 1 by 10. Okay. So, this is probability of, this is going to be your z distribution, right, normal 0, 1. So, probability of z greater than 10 times c plus 1. Okay. So, that will be 1 minus fc of 10 c plus 1. Okay. Once again, a simple calculation. Notice before we did not have this factor 10. This factor 10 came because I look at 100 samples and do the, I am doing the sample mean of that as opposed to just one sample. So, notice how when I increase the number of samples, okay, my significance level is going down sharply. Now, if I pick c equals 0, notice what happened before. For c equals 0, right, which seemed like a reasonable value, look at the alpha here. So, the alpha works out to be 1 minus fc of 10, okay. So, let us look at c equals 0. So, I get alpha to be 1 minus fz of 10. So, remember z is what? It is a standard normal, right. So, it is a standard normal. So, if you look at fz of 10, 10 is gone all the way out there. So, fz of 10 is very, very close to 1. Okay. So, the value of alpha will drop dramatically. It will be very, 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 very low, some 10 power minus 10 or something. I mean, very, very low value for alpha for c equals 0. So, contrast with the case where you did one sample. When you did just one sample, you got 1 minus fz of 1. Okay. So, notice how multiple samples is improving your significance level dramatically, right. It is reducing your type 1 error. Okay. So, that is the power of these multiple samples, and that is important to understand. Okay. So, you can find beta also, it is the same sort of power also, the same sort of calculation, probability of t greater than c given mu equals plus 1. The only thing that will change here is probability that z is greater than 10 times. So, you will have to do minus 1 here, right. So, because mu is plus 1, so it will be c minus 1. Okay. So, if you do this again, you will get 1 minus fc of 10 times c minus 1. So, once again, if you put c equals 0, you are going to get power that is very, very close to 1. Okay. C equals 0, 1 minus beta is going to be 1 minus fc of minus 10, and notice minus 10 is somewhere way out here and fc is close to 0. Okay. Very, very close to 0 here. Okay. So, this guy is very, very close to 1. This guy is very, very close to 0. Okay. So, the power tends to 1, power becomes close to 1. So, you almost have the ideal thing that you want, right, by picking c equals 0. As you keep increasing the number of samples, instead of 100, if I have n samples, then instead of 10 I will get root 10, right. So, and then c equals 0 seems to give you a really powerful way in which it is falling down. Your alpha is going down to 0, your beta is also going down to 0, 1 minus beta is going to 1. Okay. So, it is the best of both worlds. As you keep increasing the number of samples, this test looks like a wonderful test to distinguish between two different means, minus 1 and plus 1. Okay. So, once again I want to emphasize, once the sampling is given, once the null distribution is given, once the alternative distribution is given, once the test is defined, finding the significance level, finding the power is not too bad, and you can have some threshold values in the test. Typically the test will have a threshold value that you have to determine, and as you keep varying that threshold value, your significance level and your power will keep changing. Okay. So, these are constant themes that will show up again and again in hypothesis testing. Okay. That is the end of this problem solving lecture. Thank you very much.